Every chip layer gets polished mirror flat before the next one can be printed. Not smooth the way glass is smooth, flat to within a few atomic layers across a wafer the size of a dinner plate. If that polishing step fails, every circuit pattern deposited on top of it fails too, and there is no going back. China runs that step in its fabs right now. Domestic suppliers exist. The equipment is running. But take that drum of polishing chemistry and trace it backward through the supply chain, ingredient by ingredient, particle by particle, and the map ends outside China. Before you set that aside as another niche materials story, consider what kind of dependency this actually is. Chemical-mechanical planarization slurry is not a tool you buy once and install. It is consumed continuously. Every day the fab runs, replenished on a rolling cycle the way a restaurant replenishes cooking oil. A fab's relationship to its slurry is less like owning a machine and more like depending on a water supply. You do not think about it until the quality changes, and by then the problem is already in your product. China has built fabs, domesticated photoresist and specialty gases to varying degrees, and worked hard to localize equipment. If the highest grade polishing chemistry still arrives in imported drums, that is a recurring chemical dependency quietly running underneath the entire program. One that does not appear in export control headlines because it has not yet triggered a public disruption. By the end, you will understand exactly why the finest grades of this chemistry are hard to replicate, where China's domestic capability actually stands, and why the gap between what China can make and what the leading edge demands is structural rather than incidental. The chemistry map ends somewhere. The question is what it takes to extend it. This is not a story about one chemical. It is about the layer of the supply chain that sits beneath the tools, beneath the deposition systems, beneath even the photomasks. The consumable chemistry that every fab on Earth needs replenished every single day. So what is actually in that drum, and why does it matter which country formulated it? CMP slurry is not a generic abrasive. It is a precisely tuned chemical system, and the tuning differs depending on what material you are polishing and how fine the features underneath are. Think of it like sandpaper grades. Except the grit here is measured in billionths of a meter. The abrasive must be chemically inert to everything except the specific material you are removing, and one rogue oversized particle can scratch a pattern so fine you cannot resolve it under an ordinary microscope. A scratch at that scale does not just damage one feature. It propagates through every layer printed on top of it. The die is gone. The major abrasives are cerium oxide, fumed silica, and alumina, each matched to different layers. Cerium oxide handles oxide polishing. Fumed silica handles certain dielectric layers. Alumina is used for tungsten, but the particles themselves are only part of the system. Surrounding them is a package of specialty organic additives, surfactants, corrosion inhibitors, complexing agents, oxidizers, that control which materials get removed and which do not. That selectivity is what separates a usable polish from a catastrophic one. At mature nodes, the tolerances are forgiving enough that achieving acceptable slurry is a solved problem for a competent chemical company. At leading-edge nodes, where features are smaller than many proteins, the tolerances are not forgiving at all. The question is not whether you can buy particles from a chemical supplier. The question is whether you can synthesize them at the required purity and size uniformity, at volume, consistently, across every production batch. That is where the gap opens. Domestic Chinese slurry companies are real. Anji Microelectronics and Beijing Hanhua are reported to serve mature node fabs inside China, and that is not a trivial achievement. Mature nodes, the process generations used for automotive sensors, industrial controllers, power management chips, and the bulk of high-volume consumer electronics require real chemical competence to supply. China's floor has risen, but industry reporting consistently places leading-edge slurry, the grades needed for the most advanced logic and memory processes, in the category of primarily imported chemistry. No confirmed share figure is available, and the self-sufficiency claims that circulate come largely from company announcements and Chinese industry media rather than independent benchmarks. The honest framing is qualitative. Mature node domestic capability is real and growing. Leading-edge capability is not confirmed at volume. What makes the frontier grades hard is not a single missing ingredient. It is the combination of ultrafine particle synthesis and proprietary additive formulation. The highest purity ceria and fumed silica used in leading-edge slurry trace to foreign chemical lines. Cabot Microelectronics, which became part of the CMC materials ecosystem, Fujimi in Japan, and Ferro, now part of Entegris. These are not companies that simply sell particles. They are companies that have co-developed their formulations over years alongside the most advanced fabs in the world, iterating the chemistry as each new process generation created new polishing challenges. That accumulated process knowledge is not written down in a form you can reconstruct from analyzing a drum of finished product. You can reverse engineer the bulk chemistry. You can measure the particle size distribution and the approximate additive concentrations. What you cannot easily reconstruct is the synthesis process that produces particles at that uniformity batch after batch, or the interaction effects between additive components that took years of wafer-level testing to optimize. Process knowledge is harder to copy than product. Now here is the part that makes this dependency harder to escape than it might appear. And it has to do with which side of the supply chain the problem sits on. Applied Materials is the leading global supplier of CMP polishing tools. The machine that holds the wafer, applies pressure, and runs the slurry across the surface. China has faced restrictions on some Applied Materials equipment, and domestic Chinese toolmakers, Nora and Huatzing among them, per industry reporting, have been developing CMP equipment of their own, with maturing capability at some process tiers. It would be reasonable to assume that if China domesticates the tool, the slurry problem shrinks. It does not. The tool and the slurry are separate supply lines with separate expertise requirements. Owning the espresso machine does not mean you can grow the beans. A domestically built CMP tool still requires a continuous replenishment of qualified slurry. And qualifying a new slurry formulation at an advanced fab is not a matter of matching a chemical specification on paper. It requires months of process integration work, running real wafers through the polisher and measuring yield, defect rates, and layer-to-layer registration across hundreds of process variations. That qualification work is done against a moving target, because every new node generation changes the requirements. A slurry qualified for one generation may need significant reformulation for the next. Equipment self-sufficiency and chemistry. Self-sufficiency are decoupled, and the decoupling is structural. Where does that leave China's actual fab operations? The honest answer is more nuanced than the headline. The bulk of China's current fab output runs on mature nodes, the process generations where domestic slurry is increasingly viable and where the strategic exposure from import reliance is real but not immediately acute. The fabs building automotive chips, industrial controllers, and consumer electronics at scale are not currently bottlenecked by slurry chemistry. The dependency grows acute only as leading-edge ambitions scale, which is directionally where China's program is headed, but not yet the dominant operational reality. The people who will tell you China is comprehensively blocked by slurry are overstating the case. The people who will tell you this is a minor consumable easily replaced are understating how the gap actually works. CMP slurry is one instance of a pattern that runs through the entire consumable chemistry layer of semiconductor manufacturing. Capital equipment gets the headlines: lithography machines, etch tools, deposition systems. But consumables are the hidden recurring layer: photoresist, specialty process gases, CMP slurry, cleaning chemistry. Each is consumed and replaced continuously. Each has its own chemistry map with its own frontier. China's photoresist supply at advanced nodes is heavily import-reliant, primarily from Japanese suppliers. That is documented and established. The slurry story rhymes with it. The deeper mechanism is this: leading-edge process chemistry is not developed in isolation. It is co-developed between chemical suppliers and the most advanced fabs in the world, in Taiwan, South Korea, and historically in the United States. The supplier learns what the next node needs because it is running experiments inside the fab. The fab learns what the chemistry can do because the supplier is iterating formulations against real process data. China's exclusion from that frontier ecosystem creates a compounding effect that goes beyond any single material. It cannot co-develop the next generation of slurry because it is not running next-generation processes. The chemistry map and the process map advance together, and access to one without the other leaves you tracing a road that ends before the destination. Building a taller structure without access to the engineers updating the safety code means you can build high. But the rules you are building to are already behind where the frontier sits. Here is my honest read. The triumphalist version of this story, that China is permanently blocked, that slurry is an insurmountable wall, ignores a real track record. Chemistry gaps close. China compressed timelines in solar panels and batteries that the industry did not expect to close so quickly, and it has genuine research infrastructure and state investment capacity. The dismissive version, that this is just a solvable commodity problem that any competent chemical company can formulate its way to parity in a few years, ignores what leading-edge slurry actually is. It is not a static formula waiting to be copied. It is a co-developed, continuously advancing system tied to process generations that China is not yet running at the frontier. The real constraint is not the chemistry itself. It is the co-development ecosystem that advances the chemistry with every new node. That takes longer to replicate than a formula. China has drawn its chemistry map with increasing accuracy. The mature node road is paved and increasingly domestic. At the leading edge, the map still ends at a foreign border, and that border moves forward with every node generation that advances outside China. So here is the split I keep coming back to. Either the leading-edge slurry gap is a durable structural constraint that will measurably slow advanced fab timelines for the next decade, because the co-development ecosystem cannot be replicated quickly and the target keeps moving. Or it is a solvable chemistry problem that domestic investment will close faster than the industry expects, the way China compressed timelines in solar and batteries, because particle synthesis and additive formulation are ultimately engineering problems that money and focus can solve. Which of those matters more for how this plays out? Drop your honest red in the comments. I want to know which side you are on and why. Subscribe if you want to follow how China's consumable chemistry layer, slurry, resist, additives, and the materials nobody talks about until they matter, either closes or stays open as the node race continues. One drum, trace it back far enough. For now, the road still ends somewhere else.